We're going to increase our knowledge and understanding about geometric sequences in this video. In previous videos we've looked at arithmetic sequences and sequences in general. So looking more in a more focused manner at geometric sequences, we can see a sequence here, and if we looked at it based on what we've seen before, there's no common difference here. There's there's 4 there, and that's 12. So and that's way big. So we've got 36 there. So it's not going up by a constant increase. Instead, it's actually going up by a constant multiple. 2 times what is 6? Well, 3. 6 times 3 is 18. 18 by 3 is indeed 54. So we don't have a common difference. We have what's called a common ratio. So common ratio is the common word for it. So there's a multiplier there that is constant. So a multiplier instead of something that's added on. However, we do have a starting value. We have a term 1, and we just have discrete terms, and it's a list like the other sequences. So the main difference is we have a multiplicative effect due to what's called the common ratio and not an additive effect. So these won't behave like in a linear manner like the arithmetic sequences did. They'll behave, well, it's going up by increasing amounts. So what will it look like? It might be some sort of curve. Let's check it out. I've plotted those points there, and to give them a bit of a coordinate situation happening here, I've called it term 1, term 2, term 3, term 4, and the term numbers the independent quantity, and so that's gone across the bottom, and the outcome of that goes vertically because it depends on the term number. And so you can see that we've got a non-linear shape. It seems to increase its steepness as it goes. And if you've ever studied exponential functions, you'll notice that an exponential function often has that characteristic shape. So it's exponential in nature, in its nature. So not linear. As we saw with arithmetic progressions, it was linear, like a linear function, straight line. This is exponential in nature. So we have a multiplier. Let's formalize this. So a sequence in which each successive term is found by multiplying the previous term by a fixed amount is called a geometric sequence. So successive means the one after the next, the next, the next, the next. So geometric sequence has a recurrence relation in this form. So that means to go from one term to the next, we basically get the previous term, that's t sub n minus 1, multiply it by this common multiplier, this constant multiplier, this fixed amount, and you get the next term. Okay, or another way of looking at it, to get the term that you're at, you would have had to have gone the previous term times by that fixed amount. And the one we just looked at is an example of a geometric sequence. So the common ratio is a constant. So conceptually that's very important. So the recurrence is in that form there. And remember that R is a constant. Also important down here is how to get a certain term in a geometric sequence. Now you might remember from our arithmetic sequences we often had to perform tasks where we were after a specific term, and that's a common requirement in sequences. So for a geometric sequence, to get a particular term, which has term number n, you get the first term and multiply it by that common ratio r, and you raise it to the n minus 1. As I said, r is called the common ratio, and if you get two successive terms, you get basically the current one divided by the previous one, you get r. And this is probably the most common way of seeing that formula. So to get a certain term, we get the first term a, multiply it by r to the n minus 1. That's quite important. As we saw on the graph, it's exponential in nature. Let's go back to the geometric sequence we saw just before, and let's find the 10th term. So you could do it the long amateurish way, but let's do it using a more advanced mathematical method, because I could ask for the 100th term, right? So I'll ask for the 10th term here, so that would be in our formula t sub 10 equals a times r to the 10 minus 1 in this case, if we want to find the 10th. So a is the first term, a equals 2. Common ratio we determined before, the multiplier going from one successive term to the next is 3. We're ready for business here. 2 times 3 to the 9. Now remember your order of operations, you need to raise it to the power before you multiply. And then we need to grab our calculator. 39,366 I get. So you can perhaps now see that that would be far greater increase across 10 terms than a arithmetic progression with a common difference of 3. You'd have nothing like that sort of magnitude of number. So that's the difference between something exponential in nature over a certain domain compared to something that's linear in nature over a certain domain or interval. To finish off, let's look at a question. We've got a geometric sequence, and the first term is 18, the fourth term is 144. We need to find the common ratio. So let's tag these things. It's geometric. That means a equals 18. T sub 4 is 144. We have to find r. So ar to the n minus 1, and we've got 18 r to the, okay, let's have a look. We know that in this case we have 144 when n equals 4, so we can use that instance, and that would make that 3 because that's 4 minus 1. So then we need to divide by 18, and r cubed is 8, so we've got the cube root of 8, which is 2. So the common ratio is 2. This particular one we could test that too, because it should go 18, 36, 72 and 144, so that one's quite an easy one to test. So geometric